the next round about 60 minutes, I want to demonstrate you a little bit what we can do with our Cyprotec digital twin and how to test the 7SS85. So these are, the mini agenda of the next 60 minutes. So I want to start with some stable conditions, injecting values with stable condition, and demonstrate you the disconnected image in the web browser view, and give you, of course, a general introduction about our digital twin. And then I will come to some fault scenarios. I want to start with an internal fault scenario, then come to an external fault with breaker failure protection, and then come to a fault in the bus coupler dead zone.
And it will be a very good repetition of the explanation of the different algorithms, of the 1 out of 1 algorithm, of the 2 out of 2 algorithm, and also how the circuit breaker failure protection will work.
Exactly. Okay, so Gert, can you please show my screen? Thank you. So this is the digital twin overview, but first things first. Under project, you can here with this button plus sim upload your sim file. So this is what Rainer exported, can be imported here with this button. I have already prepared this and upload the 7SS85. And here this is also a nice feature of the digital twin. You can select the device firmware and the communication firmware with which the device is running. And this has the advantage that, for example, if there is a new version released and you want to retest something, compare the old version with the new version or something like that, then you can just simply change here the firmware version, and without any effort you can test different firmware versions. Under test files, it is possible to upload COMTRADE files and XML files. So this is also helpful if you want to retest a fault scenario. You can just upload the COMTRADE file via this plus button here. Or, for example, if you want to test a sequence that you created with the Omicron state sequencer, you can upload it also here as XML file. And for our demonstration today, I also prepared some COMTRADE files for the different fault scenarios. So here you can see different files are already uploaded for some internal faults, for a couple of faults. And this is a nice feature to test some things here with COMTRADEs. And under routing matrix, under this tab, then you have to make the connections between the COMTRADE that you uploaded and the input of the device that you simulate. So for example, if I go here to the test scenario internal fault and go to the current view, and so in this case the source would be the uploaded COMTRADE file and the destination is the simulated device, and then you can set here via this matrix the connection between the COMTRADE and the device. And if your device is uploaded, your test files are uploaded and the connections are done, you're good to go and start the device by just selecting the device you want to simulate and use this stop button here on the top. And this is also what I already did in the break. So we have here now our simulated device running. And on this surface here, it is possible to directly inject current and voltages and to inject binary inputs. And you can, if you change here something, you can save these values that you entered here to simulate. You can save them. And here I also created some different scenarios. I will come to this later, what I prepared here. And with this button, you can inject the values that are displayed here. So with this first button, you can apply changes automatically. So as soon there is a change made and this button here is pushed, then these changes will be sent to the device. and can deactivate it again if you don't want to have this option. The other option here is to send to apply this value manually. So if you change something, then you have to press this button to send this value to the device. With this button you can reset the values, and with this pause button you can stop injecting values. And here under these options, then you have the possibilities to select the ComRate files that you uploaded before, and to select the stable conditions or safe conditions that you saved earlier here from this direct injection. Okay, so I would say, Gerd, can you please give me the slides again? And I will demonstrate you what are the stable conditions I want to demonstrate. So the first one here is the scenario stable system, coupler closed. So here I am checking 1 amp in bay 1 flowing towards busbar 2, also 1 amp in bay 2 flowing towards busbar 2, and then these two currents are flowing through the coupler and away from the busbar in bay 3 and 4, also 1 amp for each bay. So this is called later on stable system coupler closed. The second condition here is with the coupler open. So in this scenario there's 1 amp flowing towards the busbar 2 in bay 1 and 1 amp flowing away from busbar 2 in bay 2. And same for bay 3 and 4, so 1 amp flowing towards the busbar 1 in bay 3 and 1 amp flowing away from busbar 1 in bay 4. And I also want to demonstrate a disconnector shunt. So here in this example in bay 1, both disconnectors are closed, and under these conditions it is no longer possible to trip the two bus zones selectively. So here it is like one overall zone, and in this case it is all colored in red because the preferred system here is the busbar 1. Okay, so much about the theory. Jumping back to the digital twin, please. Thank you. And now I want to show you real quick these two stable conditions I prepared. So let's start with the coupler closed scenario. So I just select here this pre-saved condition. And here, of course, also these binary values are set like displayed in the single line on the slide. So I sent this value to the device. And now I want to go to the online web browser. Okay, just redo the login again. And I want to show to you the single line diagram. So this is here, single line. And now you see exactly the colors as Rainer also has chosen before. So busbar 1 in red, busbar 2 in green. And the bays are assigned as shown on the slide before. So bay 1, bay 2 are connected to busbar 1, the coupler is closed. And bay 3 and bay 4 are connected to busbar 1 in red. And here on the bottom you see the injected current values for all the CTs. On the right side you see the differential and restraint current for the bus zones.
And you see also, unfortunately, well-known issue in the web browsers that at the moment the differential and the restraint current of the coupler zones are not available. It's available if you go to the online monitoring in Dixie 5, but due to a defect, it's at the moment not available in the web browser. Online monitoring, it will be fixed soon.
Exactly. And the checksum, last but not least, is visible. Okay, so let's change the condition. So I go from coupler closed to coupler open and apply these values. And then you can already see now the coupler disconnectors and the coupler circuit breaker are open. And now the current would be flowing like this, so towards the busbar 2 in bay 1 and away from busbar 2 in base 2 and the same for bay 3 and bay 4. So you can keep these two stable conditions a little bit in mind, because these conditions are always the pre-fault conditions in the test cases I demonstrate later. But last but not least, in the single line view, I also wanted to show you a disconnector shunt. So therefore I go to the binary inputs and, yeah, for example, go to the bay 1 binary inputs. Here you can see at the moment the disconnector 1 is in position closed. The disconnector 2 is in the position open here. So I remove the open high signal and activate the checkbox for the closed high signal and send this to the device. And now you can see everything is red, because here in bay 1 we have this disconnector shunt. And as I told earlier, it is no longer possible to selective trip the bus zones. So here, of course, we only have the differential and restraint values for bus zone 1 and no longer for 2 separate bus zones. Okay, so I think we are good to go to test the first fault. And Gert, please give me the slides again. Keep the studio team busy here. Thank you. So this is what I want to demonstrate first. 3-pole internal fault on busbar 2 with a high fault current. So these are our pre-fault conditions as explained earlier, with the coupler open. And then let's assume there's a fault on the busbar 2 between bay 1 and bay 2. And this leads to a current that is increasing and now flowing from both directions towards the fault. So I increase here the value from 1 amp to 5 amp and turn the direction of the second CT around. So both currents are flowing towards the busbar now. And for the busbar 1, everything is still stable. So we only want to simulate a fault on the busbar 2. Okay, thank you, Gert. So we start with the stable condition, coupler open. And I want to replay the ComTrade internal fault.
1 of 1.
1 of 1. I think will get clearer later why I named it 1 of 1. So I press this start button to replay this ComTrade. Okay, you already see here are some red LEDs glowing for the operate A, B, and C. So we have a 3-pole fault.
Maybe you read it's maybe too small, but the LEDs, the meaning of the LEDs, maybe you can read them.
It's the operate general from the bus differential and the operate phase A, B, and C.
Okay.
Okay, so as you can see, the disconnectors are now in intermediate position because the ComTrade file is finished. So yeah, to change it back from intermediate to stable conditions, I just go back to my prepared current values to fix this. Okay, everything fine again. So yeah, let's take a look at the fault that we tested. And therefore I go to the web browser again. And this time I go to the fault log in the web browser. So I open the fault log and take the one with the newest timestamp, so number 2 in this case, and scroll down because it is sorted from newest to oldest. So the newest one is the top one, the oldest one is the one on the bottom. So here we go, and we see there is a busbar fault on bus zone 2, and phase B and C were the first one that give this operate. And as we have a fault on the bus zone 2 and bay 1 and bay 2 are connected to bus zone 2, these are the two bays that are receiving a trip command. And this is what you see here. And of course, also, as we have a busbar trip, the inherent circuit breaker failure protection picks up. And these messages here are also worth to mention because they show the position of the disconnectors and the circuit breaker at the time of the trip. So this helps later on to analyze this fault and check, okay, which disconnectors were closed at the moment of the trip and which were open.
So typically when there's in the reality a busbar fault, so that means a whole bus zone has been tripped, all the management and the operational staff have to work to bring power to all consumers once again, and they will switching the disconnectors to ensure the power to all consumers. And when this is reached, then will start the analysis what really happened. Was it a wrong trip by the busbar protection? Mostly not. What really happened? And to make this investigation, it's very helpful to know really how was the disconnector image, which feeder was assigned to which bus zone at the moment of the trip to make the analysis and really to log this information we implemented to give the position at the tripping time and save it in the fault log.
Okay, let me do a quick step before I download the record because I don't clear my download folder so that you don't get confused. Okay, now let's have a look at the fault record. So I go to the web browser again and to the home button, and this time I jump to recording. So here, of course, I'm also interested in the fault number 2. It is possible to display this fault record directly in the web browser, but today I want to download it and open it directly in SIGRA, so offline. And therefore I use this download option here. Take some seconds. Okay. And then I go to this download folder, and here is our newly downloaded CFG file. Open it with double click, and now you see the currents in SIGRA. And the first question I want to clarify is why only phase B and phase C pick up at the beginning and not all 3 phases at the same time, for example. And therefore I want to put all the phase currents in one diagram. And this is possible by simply select the signal and drag and drop it to the first diagram in this case. And I do the same for the phase C current, so click on this and drag and drop. And of course this is a little bit small now, so I increase the diagram height to 100 millimeters. Give SIGRA some time. It is a big record, so of course needs a little bit. And now I want to zoom in.
Looks very nice.
And I think now it is, yeah, almost at the first sight is getting clear why phase B and C are the first one to operate. Phase B is here the blue one, phase C is the green one, phase A, of course, then the yellow one. And here you can see, if you compare phase B and phase C with phase A, you can see that those 2 phases have really a higher slope, a greater slope than the phase A. And this, of course, have an influence that on the trip time, I would say. Okay, then second step, I want to have a look at the differential and the restraint current. And the fault happened on bus zone 2, so I scroll down until bus zone 2 comes. Let's check. Okay, I think here we go. Yes, this looks good. And I we'll have a look at the values of phase B in this example. So I just want also to have the restraint and the differential current in one diagram. So I put this here and optimize a little bit and increase once again the height of the diagram.
Okay, zoom a little bit out once again, I would say.
Yes, as soon as Sigra is finished.
Oh, still working.
Still working. Yes, now we good to go.
Here, while Nina is zooming a little bit out, it's once again, I want to repeat what I have already stated in our last tutorial. In SIGRA, in every folder record, we see at one side the differential current. The differential current, that's a green one, and the restraint current is not the calculated restraint current. If you remember, I have explained we are working not with the calculated restraint current. The algorithm is every time working with the so-called modified stabilization current. The modified stabilization current is the same like the calculated stabilization current. As soon as the calculated stabilization current is higher or is increasing, as soon as the calculated stabilization current is decreasing, it's not going sinusoidal decreasing, it's decreasing a little bit in a linearized way. You see it here, this decreasing after the zero, after the black line. That's no sinusoidal decreasing. It's really this decreasing in this linearized, modified way. Exactly, and go when it's increasing again. Yes, and here once again the calculated stabilizing current is higher than the modified, and then it's decreasing again. But still more, we are seeing here not the modified stabilization current, we are already seeing the modified stabilization current multiplied with the stabilization factor. Means if the differential current is above here really the line in the fault record, we can directly state we are in the tripping area. So as soon as the differential current is above the characteristics of the modified stabilization current multiplied with the stabilization factor, we can say, okay, we are in the tripping area. Okay. Mm-hmm. And okay, so I will continue. And once again, if you remember, the 1 out of 1 algorithm, the 1 out of 1 algorithm has to be triggered by a jump of the stabilization current. And you see here, maybe once again, what are the numbers on the epsilon on the y-axis? It's I guess here that's 10.
This is 10, yes.
That's 10. So you see here really a very big jump. So we here from the blue line under the black line, it's 1.5 milliseconds. So that means we have a jump of the stabilizing current within 1.5 milliseconds of nearly 10 times the nominal current. And this is even multiplied with the stabilization factor. So that means that's really a jump higher than 10 times the nominal current. And at the same moment, we are in the tripping area. That means from the very beginning, the differential current is above the restraint current multiplied with the stabilization factor. So that's really a clear indication this will for sure trigger a 1 out of 1 trip by the busbar protection. And from the fault inception, so that's here at the blue line, here that's around the fault inception. The black line, that's 0, that's the tripping. Of course, the tripping of the algorithm without the delay of the binary inputs. So the algorithm has seen this tripping within 1.5 milliseconds in this case. Okay.
Okay, and this is happening with the 1 out of 1 algorithm, and this is why I called this test case internal trip 1 minus 1. Okay, enough about this fault. I need the slides again, please. Exactly. So we are now looking at a one-pole internal fault on Busbar 2 with a small fault current. So the starting conditions, the pre-fault conditions are exactly the same. We have these stable conditions, coupler open, and now what happens is a fault on Busbar 2, same position. But in this case, I only want to simulate a small fault current. That means I don't increase the values, and I only want to simulate a one-pole fault. And that means I just change the direction, as you can see here in bay 2, of phase A current in bay 2. So now there is a current flowing towards the fault in bay 1 and bay 2, but only with an amplitude of 1 amp and only for phase A. Okay, thank you, Gert. So I close this record and go back to the digital twin. Okay, as I said, I want to start with the pre-fault condition coupler open. So I inject these values and clear the LED so that we can check that everything is fine at the beginning of the fault. And now I select the ComTrade file internal fault 2 minus 2 and replay this record. And here you may already see the difference. Now we only get here this operate signal LED for phase A. Okay, now it's finished. I jump back to the stable conditions. And we will have a look at the fault. So I go back to the web browser and home. And here I open the fault log in the first step again. Fault log, and now this is fault number 3. I scroll down to the bottom, delete here this download information. And now we can see here, once again it was bus zone 2, and of course the check zone that trips, but only for phase A. Of course the trip is nevertheless a 3-pole trip, but here this fault was only triggered by phase A. And of course here once again the trip signal is issued to in bay 1 and bay 2, because these are the 2 bays that are connected to bus zone 2. And of course in this 2 bays also the inherent circuit breaker failure protection will start simultaneously. So much about the messages. Now I want to open the record again. So I go to recording and fault recorder and download this time the fault number 3. Okay, everything is finished. I go to my download folder and open the record number 3.
Maybe now we can see a 2 out of 2 fault, or?
If everything went right, yes, we should see a 2 out of 2 fault. I don't want to talk much about the phase current, just a small hint. Here you can see in the phase A current that the amplitude stays the same, but the phase changes. You can see this here. But now I go directly down to the differential and the restraint current, once again of bus zone 2. Scroll down a little bit. Bus zone 1, really a lot of signals for busbar projection here. Bus zone 2, and now of course we are looking at the phase A current because this is the one where the fault happens. So I put this in the same diagram, double click on the diagram to increase the height. And of course zoom in as soon as SIGRA is finished.
So now we can analyze the 2 out of 2 algorithm. And if you remember correct, the 2 out of 2 algorithm will be triggered for the first threshold exceeding when the 1 out of 1 algorithm can't apply. Means that we have no jump of the, oh, thanks, Red, very nice. So that the jump of the stabilization current. So maybe let's start with the jump of the stabilization current. The stabilization current is a blue one, and I think it's very clear that we have absolutely no jump of stabilization current. So a 1 out of 1 algorithm is not possible. And we see here, maybe once again, here at the beginning of the fault. So here, not the beginning of the fault, when really the differential current starts. Okay, and then the 2 out of 2 algorithm will be triggered when we have the first threshold exceeding. Maybe we can really here step by step. No, okay. Yeah, okay, it's fine. And here we have the first possibility, and here a little bit on the right side, to be a little bit more realistic. And now we will start the 2 out of 2 algorithm. And if you remember, the 2 out of 2 algorithm, 1 threshold exceeding is enough. But to be sure to start the second, to make a measurement window in the second half wave, we are starting and rest and break of the measurement of 8 milliseconds. And now I can't read it, so we have between the yellow and the blue line 8 milliseconds?
Yes, yes.
The state time 8 milliseconds is for 50 Hertz. Of course, we are testing here with a 50 Hertz system. For 60 Hertz, it would have been 6 milliseconds. And after the state time of 8 milliseconds, we will have a measurement window of 6 milliseconds. And within the 6 milliseconds, we need 4 threshold exceedings. So you can see at the very beginning, when the measurement window will be opened again, we will have no threshold exceedings. So it starts here, Nina, you can sign when, okay, here beginning from this moment, we will have a threshold exceeding it again, and then we need 4. I think could be quite fine. So that really at the tripping times, there should be 4 threshold exceedings possible. So all in all, if you maybe once again with the blue cursor go at the beginning of the fault and set the time, now it's 18, or I can't read it.
16.5.
16 milliseconds. Really the tripping time of the 2 out of 2 algorithms, plus roundabout 4 milliseconds for type F binary outputs. So we have overall tripping time of the 2 out of 2 algorithm of 20, 21 milliseconds, depends on. Okay, now we had also a very fine repetition of the 1 out of 1 algorithm and the 2 out of 2 algorithm.
Okay, then slides please. Thank you. So the third scenario I want to demonstrate is an external fault in bay 4. So we start once again with the stable conditions with the coupler open, and there's flowing current towards the busbar in bay 3, over busbar 1 and away from the busbar 1 in bay 4. And now let's assume here is a fault, and the current, for example, increases, that is flowing towards the fault, and we receive a start signal for the circuit breaker failure protection, because, for example, a remote and differential protection system tried to trip this line and the breaker failed. Okay, thank you, Gert. So close this record and jump back to the digital twin. So stable condition, coupler open are once again our pre-fault condition. So I check these values and clear the LEDs. And this time I don't want to demonstrate this by replaying a record, but directly changing the values that I apply here. So I was talking about a fault in bay 4, an external fault in bay 4. So I change here, go to this site for bay 4, and we say we increase the current that is flowing towards the fault. So I increase the number here from 1 to 3. And if you have these buttons here activated, he automatically chooses the same value for all 3 phases, and he will also balance the angles correctly. If you want to change one should change it individually, you can just deactivate this box, and then you can change each value separately. But in our case, we leave it like this. So I apply these values, and then we go to the binary signals. Of course, in a real case scenario, it wouldn't take that long, but I think we are okay for this test. And then I have to search the right binary input signal. These are a lot.
This will be the most challenging part for today.
So we are talking about bay 4, and luckily I practice it. So here it is. We are in bay 4 in the circuit breaker, and this here is the circuit breaker failure start signal. So I activate this checkbox here and send these values to the device. And you see here now we get this 3-pole operator once again. I can deactivate it, send these values again, and let's have a look what happened. So I go to the web browser once again and open the fault log in the first step. So now it is fault number 4. I scroll down to the bottom, and now we see here the circuit breaker failure protection pickup, and 50 milliseconds later there comes the retrip of T1, and in parallel the T2 timer is started, and we see here this T2 time elapses, and we get the operate, in this case, from bus zone 1. Once again, in phase B and C first, but phase A will sure come later. And assigned to bus zone 1 is bus bay 3 and bay 4. And of course, these 2 bays are the one that will trip.
And just to remember, we have selected the breaker failure protection mode of unbalancing and not the IQA. And this will be interesting when we have a look in the fault record.
Exactly, and this is what we're doing right now. So I go to recording here and download the ComTrade file of fault number 4. Good, this time I want to start by looking at the binary signals. Okay, I don't know how good it is to see for you. Here, interesting is the circuit breaker start signal. So this was the binary signal that we activated. And here is the retrip T1 after...
After who?
I use this cursor here to the start of this signal, and of course the second one to measure a difference, and then you see this 50 milliseconds, and this is of course what we set here. And let's go to the trip T2. This should be 130 seconds, and I would be surprised if it would be something different. So now here we have these 130 seconds as the delay for T2. And yeah, really not much later comes the operate of the busbar protection. But let's have a look at the differential and the restraint currents. This time it happens in, the trip happens
maybe,
in bus.
once again, before we go to the differential current, do you have now the yellow cursor on the trip T2?
The yellow
Yes,
cursor
okay,
is
so
52.
exactly fine, because the trip T2 now will stimulate the unbalancing of the bay current. And so let's see how the timing is.
Okay, bus zone 1 was the one that was relevant for this fault. So let me just scroll to the bus zone 1. And here, yeah, maybe we just look again at the bus of the phase B or C, because this was the fast ones. I select here phase B and put it in one diagram once again. And increase the height. And zoom in. Now maybe we need the operate time also as a reference. The operate of the busbar protection. So I put this cursor here on the operate of phase B, and the yellow cursor is on the trip T2 signal.
But I'm a little bit astonished in this example, because we have seen it a lot of times on a different way. I do not know, maybe the timing of the digital twin. It's a little bit surprising that the differential current already starts before the trip T2. I do not know the reason at the moment. Normally, the differential current should start immediately after the trip T2, but not before. But okay, this may be a reason also in the timing of the simulation. I do not know. Normally this should not happen. Okay, but here with the trip T2, the unbalancing will start, and before it was external fault only, and via doing this unbalancing, we will how to simulate it to an internal fault, so that with the mechanism of the busbar differential protection, we will trip the associated bus zones. And the restraint current is the magenta one, I would say. And once again, that's very important. With unbalancing, you will never have an 1 out of 1 trip. As with unbalancing, you will have no jump of the stabilization current, because the jump of the stabilization current will start typically maybe at the beginning when the circuit breaker failure protection picks up at all, but not in our case, the delay time T2 130 milliseconds later. So where Nina already have placed the yellow cursor is when, due to the unbalancing, we have the first time the threshold exceeding. That means the 2 out of 2 algorithm will be triggered. So that's at the yellow point. And then once again, 8 millisecond dead time. So the 2 out of 2 algorithm. So here, here we will start once again a measurement window of 6 milliseconds. So for at least around about 1 millisecond, we will have no threshold exceeding. But immediately after, we will have the threshold exceedings, and at the yellow point, that's the tripping.
That's 6 milliseconds
that's a 6
later.
Millisecond, and okay, that's fine. So we see it's absolutely fine to have 4 threshold exceeding, and the trip, okay, it's a little bit later. We see here because we don't know how it is synchronized our protection cycle really with the measurements. And here is a tripping around about half millisecond later than when the measurement window ends.
6.3 it is.
Yes, okay. So here, really at this point, we will trip the associated bus zones after the unbalancing of the bay current. Okay, fine.
Okay, then let's have a look at the bus coupler faults. So here I have two fault scenarios. To speed it up a little bit, I want to explain for both cases the theory at first and then do the testing. So the first fault case would be a fault in the dead zone of the bus coupler in a 3-pole fault. So the pre-fault conditions would be that current is flowing towards the busbar 2 in bay 1 and bay 2, flowing through the coupler and flowing away from the busbar 1 in bay 3 and in bay 4. And now let's assume there is a fault here on this position, so between the two CTs in the coupler. And this means here is the fault, so the current is flowing towards the fault. So now the direction in bay 3 and 4 and in the right coupler CT changes. And now from both directions the current is flowing again towards the fault here. And this is happening 3-pole. The second coupler fault I want to demonstrate is almost the same, but 1-pole. So here completely same pre-fault conditions. And now the direction of the current in bay 3 and 4 are changing and in the right coupler CT. And now current is flowing towards the fault from both bus bars, but in this case only one phase, so only for phase A. Okay, thank you, Gert. So let's close this record and go to the digital twin. Clear these LEDs and we say we want to start with the coupler closed condition. So I select this one and apply these values. Maybe we can also have a quick look on the display. So here you can see this pre-fault condition, the coupler is closed. And now I select at first the coupler 3-pole fault and replay it. Okay, you see the coupler CT has opened. We have an operate, a 3-pole operate, of course. And now it is finished. And I change back to the stable conditions, coupler closed. And I think this time it is sufficient to only look in the fault record, in the fault log real quick. And therefore I go back to the web browser again and open the fault logs. Now we have 5 entries. The number 5 is the newest one. I scroll down to the bottom and now you see here there's the operate from the coupler zone. And since we have these two thresholds in the bus coupler differential, the first one was for 3-pole faults and it was set to 1 amp. This means as soon as we have a differential current above this threshold and for 3 phases, then we will immediately trip both bus zones in overlapping mode. And the second threshold was set to 5 amps and this was the threshold for the 1-pole faults. And that means as soon as we have exceed these 5 amps, then we will also get to overlapping mode for 1-pole faults. But in between, so for currents smaller than 5 amps.
And to 1-pole fault?
And 1-pole fault, of course. There will be a selective tripping with the end-fault protection involved. But first test scenario was a 3-pole fault, so and this is why we see here this operate for both bus zones. And let's demonstrate the second scenario. The coupler closed scenario is already active, and now I jump to the coupler fault 1-pole and replay this one. Maybe I clear the LEDs.
And now we expecting really a so-called sequential tripping, or first only tripping the coupler applying the end fault, and then only the faulty zone should be cleared.
Exactly. Okay, now it is finished. Go back to stable conditions. And you already see here it is only the LED for phase A active. And let's have a look at the fault log. This is number 6 in this case. And here you see only bus zone 1 trips finally.
Can we see the trip of the circuit breaker first? In the log? The trip open command, coupler, circuit breaker, circuit.
You mean this one?
Is this a coupler? Yeah, exactly. Yeah. Yes, it's here 384. And when then the bus zone 1 tripped?
Here.
458. Okay. Fine.
Okay. So these are the fault scenarios I want to demonstrate. Maybe just some small hints about the digital twin. Today I demonstrated the centralized setup, or we demonstrated the centralized setup. It is also possible to simulate a distributed digital twin with up to 20 devices if you have the digital twin L license.